Hello everyone. In this video, we will go over several examples about the Laplace transform. The definition of the Laplace transform is given. So first of all, we have a function f of t, which is defined for t greater than or equal to 0. And we will be representing the Laplace transform with this script L, f of t, and that is calculated as an integration over 0 to infinity. We multiply our function f of t with e to the power minus st, and the result of this integral will depend on the independent variable s, and the resulting integral can be represented as a function of this s. If this integral is convergent, then this f of s is called as the Laplace transform of the function f of t. Now let's look at some examples. We have f of t given as e to the power at. So how can we take the Laplace transform for this f of t? Well, you will apply the definition, integrate this from 0 to infinity as you see. We multiply with e to the power minus st, and this is our f. The function f is here. And you can rearrange this exponential as minus s minus a t dt. We know how to integrate the exponential. Basically, you will need to divide with this coefficient and rewrite the exponential. So we rewrite the exponential, and then we have minus 1 over s minus a. And then we write this as b goes to infinity. So if we evaluate this expression, we need to plug in, instead of t, we plug in b. And if we plug in 0, this is going to be e to the power 0. So we write that as e to the power minus s minus a b minus 1. And we still have this negative coefficient outside of this expression. And as b goes to infinity, this expression will go to 0. So we will be left with minus times minus, we have plus 1 over s minus a. So the Laplace transform we obtain is 1 over s minus a for s minus a greater than 0. We require this because, as we said, we want the Laplace transform to be a convergent integral. It should be a finite value. Here is another example. We have the function f of t equals to t, and we want to calculate what is the Laplace transform of this t, f of t equals to t. So this is our function f. We plug in into our definition, and we have t times this exponential that should be integrated over 0 to infinity. So a polynomial times exponential, this kind of expression, we can actually use the integration by parts from calculus. And in the integration by parts, we need to let a new variable u equals to this t. And then we know that if we differentiate, because we need to write du, that is going to be equal to dt. And then the remaining expression here, we can solve for v, and v is obtained as minus 1 over s e to the power minus st. So if we apply the integration by parts formula, we have u times v minus the integral v times du. So in this integration by parts formula, we just substitute these. We have u, which is just t, and then we have v, which is given here as minus 1 over s times the exponential term here. So we just plug in these, and then we subtract the integral v times du. Du is equal to dt, and v is given. So here is our v times du. And since we have two minus signs, they cancel each other, and we put a plus here. And this should be evaluated as b goes to infinity. So if you evaluate this expression, plug in b instead of t. And if you plug in 0 instead of t, then you will get 0, because t equals to 0 is 0. So this term here, the second term will be 0. And the first term, as b goes to infinity, this will also go to 0. This expression also goes to 0. So the first expression, we just get 0. The second expression, take the integral here, and then evaluate e to the power minus sb. And as b goes to infinity, this expression will go to 0. Minus times minus, we will be left with 1 over s squared. So the Laplace transform of f of t equals to t is given as 1 over s squared. We are given f of t equals to t squared, and we want to calculate what is the Laplace transform of t squared. Well, apply the definition of the Laplace transform, which is an integration. We multiply with e to the power minus st times our f. And again, in this type of expressions where you have an exponential times a polynomial expression, we can always apply the integration by parts from calculus. And in order to apply the integration by parts, first we need to define a new variable. We let u equals to t squared, and then this means du equals to 2t times dt. And then the remaining term, we assign this as our dv. And then from here, we need to integrate both sides, and we obtain our v as minus 1 over s e to the power minus st. Now we can apply the formula u times, which is t squared, this is our u, and then we multiply with the v, which is given as 1 over minus 1 over s here times e to the power minus st. And then we have a minus. In the integral, we have v times du, and du is 2 times t times dt. So we have 2 times t and dt. That is actually the du substituted in this integral. And then we have the expression v, which brings us this 1 over s and e to the power minus st. Now combining this, as the b goes to infinity, this first term will go to 0, and as b goes to, if we substitute, because first we will substitute t equals to b, and then take the limit as b goes to infinity, that will go to 0, and then we will substitute t equals to 0, but that will give us 0. So the first expression just gives 0 as a result. And if we look at to the second one, and notice that this expression is actually, this is the definition for the Laplace transform of the function f equals to t. So this is actually our f of t equals to t, and that's the definition of the Laplace transform. What we see here, this whole expression, is the definition of the Laplace transform of t. And this is calculated already as 1 over s squared. Therefore, for the Laplace transform of t squared, we will get 2 over s times the Laplace transform of t, which is 1 over s squared. And if we just put this here, we get 2 over s cubed. That's the result for the Laplace transform of t squared. In the next example, we have f of t equals to t cubed. And what is the Laplace transform of t cubed? Well, we apply the definition one more time. We plug in t cubed, and then we have the e to the power minus st. The integration is from 0 to infinity. As we mentioned before, a polynomial expression times an exponential expression, you can use the integration by parts from calculus. So you need to let u equals to t cubed and then calculate du. And also we need to write down what is v. Then we substitute into the integration by parts formula. We have u times v. This is u times v. And this must be evaluated from 0 to b. But if we plug in t equals to b, b goes to infinity. So this expression will decay to 0. And if t equals to 0, t cubed, we have again 0. And then on this expression, now notice that this is the definition for the Laplace transform of t squared. This is the definition because this b goes to infinity here. So we just write this as the Laplace transform of t squared here. And we have this coefficient 3 over s, which is written here. This gives us 3 over s times. We remember that the Laplace transform of t squared is 2 over s cubed. Therefore, we obtain 6 over s to the power 4. Now, actually you can catch the pattern here. And for f of t equals to t to the power n, you can generalize this now. And the Laplace transform of t to the power n can be written as n factorial divided by s to the power n plus 1. So this is the general formula now for the Laplace transform of a function t to the power n. Let's look at this example. Now we want to calculate the Laplace transform for f of t equals to e to the power minus kt. We will need to apply the definition as usual. So this is the Laplace transform definition. This is your f. This is our f function. And we multiply that with e to the power minus st and integrate with respect to t. So you can rearrange this coefficient here and then integrate this with respect to t. That gives you this expression. And we need to evaluate this integral from 0 to b. So if t equals to b, remember b goes to infinity, right? So the first term actually goes to 0. And then we have t equals to 0. So we have minus, and then we have another minus. E to the power 0 is 1. And then you have s plus k. So these minus signs cancel each other, and we can write it as 1 over s plus k. This is the Laplace transform for e to the power minus kt. In this example, now suppose our f of t is e to the power kt. In the previous example, we have e to the power minus kt. Now we consider plus sign, and not much changes for us in terms of the methodology. We apply the definition of the Laplace transform. We write our f. This is the f function we are interested. we multiply with e to the power minus st, and then we have the dt. So you can rearrange this coefficient here, s minus k times t, integrate this, and then evaluate at 0 and b. So if t equals to b, this is going to be s minus k times b. As b goes to infinity, that will decay to 0. But for t equals to 0, e to the power 0 will be 1. We have a minus, but then there is another minus. So minus minus, we have plus 1 over s minus k. So the Laplace transform of e to the power kt is 1 over s minus k. In this example, suppose we want to calculate the Laplace transform of cosine hyperbolic function kt. In order to calculate the Laplace transform for the hyperbolic cosine function, we can use the property that gives the hyperbolic cosine function in terms of the exponentials e to the power kt and e to the power minus kt divided by 2. So we use this property, then we can substitute the hyperbolic cosine function with the Laplace transform of these two exponentials, because we have already calculated the Laplace transform of these expressions, so we already know them from the previous examples. So if you directly substitute, as you see, you substitute this one, and you can substitute the second one as 1 over s plus k, and then just rearrange, and you end up with s over s squared minus k squared. So this is the Laplace transform for the hyperbolic cosine kt. In the next example, suppose this time you want to calculate the Laplace transform of the hyperbolic sine function, and there is a similar property for cosine and sine hyperbolic functions that represents in terms of the exponentials. So we can use this property, and here this is equal to the e to the power kt minus e to the power minus kt divided by 2. So you can substitute instead of the hyperbolic sine function and then apply the Laplace transform to these exponentials. And the good news is, again, we have already evaluated this in the previous examples that we have calculated these Laplace transforms. And you can again do the substitution one more time. This one is 1 over s plus k, and e to the power kt, we have 1 over s minus k. And basically we can do the algebra here, multiply this expression with s plus k, multiply the second expression with s minus k, so these terms will cancel, and we just end up with k over s squared minus k squared. So the Laplace transform of the hyperbolic sine function is equal to this expression. Let's look at another example. This time we have a trigonometric function cosine kt. The Laplace transform for this expression, now we can use another useful property from calculus that is known as the Euler formula. The Euler formula actually connects the exponential function with the trigonometric functions cosine and sine functions. So we have the exponential, the complex number I here, kt, is written as the cosine kt plus the complex number I times the sine of kt. And actually you can use this property and you can substitute, instead of ikt, we can substitute minus ikt, and that means our actually k is substituted with a minus sign. So instead of kt we have minus kt here, and also minus kt in the sine function. But for the cosine function, cosine kt equals to the cosine minus kt. These two are the same. Okay. But for the sine function, sine of minus x actually equals to minus sine of x. So for example, if you have the sine function, if you have a minus sign inside of the argument, you can take it out and you can write this as sine of x. So we are doing this here. And if we want to obtain the cosine kt, I mean, you can sum these expressions. So this term and this term will cancel each other, and you will end up with cosine of kt equals to the sum of these exponentials, and we multiply with 1/2. So now we can take the Laplace transform of both sides of this equation. And we apply the Laplace transform to this expression here. And the Laplace transform is a linear operator. We can actually separate this summation and take the Laplace transform of each expression. But again, the good news is we have already calculated the Laplace transform for an exponential function. So in that formula, just substitute, instead of k, we substitute I times k. So that gives us 1 over s minus ik. And for this guy, we have 1 over s plus ik. And one more time, do the algebra to simplify this expression, and you will notice that this is s minus ik, s plus ik. If these two are multiplied, you get s squared minus ik squared. But notice that I squared equals to minus 1 by definition of the complex number. Therefore, we just write a minus sign, so that becomes s squared plus k squared. So we obtain the Laplace transform for the cosine function. Now, in this example, let's find out what's the Laplace transform for the sine function. It will be similar to the cosine function. First, we can use the property from calculus, which is known as the Euler formula. And this property makes the connection between the exponential and the trigonometric functions. So we can just plug in also minus ik and rewrite this as a secondary equation. And then we multiply this equation with a minus sign on the left side, and minus, this becomes minus cosine and plus sine functions. So this time our goal is to solve for the sine kt. And that can be written in terms of this expression here as e to the power ikt minus e to the power minus ikt divided by 2 times I. And then now we can take the Laplace transform of this expression. One more time, the Laplace transform, remember, is a linear operator. So you can actually apply this to individual terms. Take out the constants. This is a constant expression we can take out of the Laplace transform, because Laplace transform itself is an integration, and a constant in the integration you can take it out. So we can take out these I over 2 values out of the Laplace transform. And notice that this 1 over 2i, the constant here is actually 1 over 2i, but you can multiply the numerator and denominator with the complex number I. So doing this expression doesn't change anything, but this is 2i squared, so this is going to be minus, there will be a minus sign, I over 2. So that's why we have this I over 2 here. We just rewrite 1 over 2i as minus I over 2. And the Laplace transform for the exponential is calculated in our previous examples. So we just use the result and we substitute the Laplace transform for each of these expressions one by one. And then do some algebra a little bit here to just rearrange, and we get s squared minus ik squared, which is equal to s squared plus k squared. And if we just simplify this, the constant 2 cancel out, and you have I squared, which is minus 1, so it cancels out with this minus sign, so eventually you get k over s squared plus k squared as the Laplace transform for the sine function. Here we have another example. We want to calculate the Laplace transform of this expression, where we have 3 times e to the power 2t plus 2 times sine squared 3t. Now remember, Laplace transform is a linear operator because actually its definition is an integration over 0 to infinity. So we can apply the Laplace transform to each expression. But notice here we have a sine square. Instead of evaluating the Laplace transform of sine square, we can substitute this with 1 minus cosine 60. Because we already know what is the Laplace transform of a cosine function. But we didn't know what is the Laplace transform of sine square or cosine square. We didn't know. We don't know it yet. So instead of evaluating, trying to evaluate the Laplace transform of the squared expression, we substitute it with a simpler one, which we already know. So 1 minus cosine 60, this is the trigonometric identity. So remember, we can write for the cosine, let's say if we have 2x, this can be written as 1 minus 2 sine of x, sine square of x. Or you can represent cosine 2x as 2 times cosine square x minus 1. So these are the trigonometric properties we might remember from your trigonometry courses, etc. So we just do a substitution to simplify this with an easier expression. And then we can write this as, now use the linearity of the Laplace transform. So we take this also constant out. And Laplace transform of exponential, we already know. We have evaluated, remember, in the previous examples, we considered e to the power kt. And the Laplace transform for this expression was 1 over s minus k. So we have k equals to 2 in this case, and we obtain 3 over s minus k. The Laplace transform of just the constant, we also know that this is going to be equal to 1 over s. But if you want to verify, you can easily apply the definition, and from 0 to infinity, you can write e to the power minus st. The constant is just 1, and then you will have dt. So the integral of this expression is 1 over minus 1 over s e to the power minus st, and then you need to evaluate this from 0 to infinity, and basically you will get the result you will get is 1 over s. So let's write it down. So that's why we have 1 over s here. That's the Laplace transform of the constant 1. And then we have also evaluated in the previous example, one of the previous examples, we have the Laplace transform of cosine k times t. And remember, this in the previous example was represented as a general parameter k. If k equals to 6, then we have s squared plus k squared, which is 36 for this particular example. Now, combining all these pieces back together, just do some algebra here, and you will obtain 3s cubed plus 144s minus 72 in the numerator. And in the denominator, you multiply these all together, and that gives you the result. Here is another example. We want to calculate the Laplace transform of 3 times sine 2t plus 4 times e to the power minus 3t. And actually, we know how to calculate the Laplace transform of the sine function, and we also know what's the Laplace transform of the exponential function. So we just need to use the linearity property of the Laplace transform and then break this into pieces. We take out these constants out of the Laplace transforms, which is of course allowed. And what's the Laplace transform of sine 2t? Here actually, if you go back to our previous example, it was sine kt. So k equals to 2, as we have used the notation previously. And basically that gives you k divided by s squared plus k squared. So that's the Laplace transform where we write in this expression. And for the second expression here, this is also in the previous example, we have e to the power minus kt. So we have s minus and k equals to minus 3. So this is minus 3. And we obtain, if we just rewrite this, the first term is 6 over s squared plus 4. The second term is 4 over s plus 3. Let's look at to the next example. The Laplace transform of this expression, sine minus cosine terms. Again, apply the linearity property of the Laplace transform. Also take out these constant terms. You can take it out of the Laplace transform. And then focus on this sine and cosine terms. And we have already, this is already done in some previous example, the Laplace transform for the sine of kt, and here k equals to 1. So we have 1 over s squared plus 1. So for the first Laplace transform expression is here. And then for this guy, we also write down this expression s divided by s squared plus k squared, and k equals to 3 here. So as you see, we can just apply the linearity and complete each piece where we know how to calculate the Laplace transform for simple functions such as the sine function, cosine function, or exponential function. Once we calculated these for some basic functions, we can consider a combination of these functions and know how to take the Laplace transform. Let's look at this example. We want to calculate the Laplace transform of 4 times t cubed 5t squared plus 2t minus 5. It's a polynomial expression, but we know each piece already from the previous examples. And then we can use the linearity of the Laplace transform and take care of each one by one. And we know that the Laplace transform of, well, actually we can write for the general case one more time. If we are given t to the power n, then that was equal to the n factorial divided by s to the power n plus 1. So this was the formula we generalized after evaluating several polynomial expressions. And you just do this. This is 3 factorial divided by s to the power 4. And then for t squared, you have 2 factorial divided by s cubed. For this one, you have 1 factorial divided by s squared. 1 factorial is just 1. And for this guy, actually, you have 0 factorial, but 0 factorial by definition equals to 1. So you have a 1 over s, and we have a 5 here, so this becomes 5 over s. And basically, by combining these all together, that gives us the Laplace transform of this polynomial. Let's consider one more polynomial for practice. So you see we have a quadratic expression, but one more time we will use this general result for the powers of t. If we have t squared, that's going to be equal to 2 factorial divided by s cubed. And we have another 3 here, so we get 6. And then what about Laplace transform of t? That's going to be 1 factorial divided by s squared. So we have the s squared here. For the constant, one more time, we have 1 over s. So we can combine this expression, and this gives us the Laplace transform for this polynomial. Now, there is another function that is useful when we are calculating the Laplace transforms. That is the gamma function. The definition of the gamma function is given here. And we use this capital Greek letter gamma of x to represent the gamma function. This is an integral from 0 to infinity. We have e to the power minus t times t to the power x minus 1 dt. And this x is greater than 0. So you can give different values to this x and try to calculate this gamma function. Of course, from here you can see if x equals to 1, it will simplify our expression because this will be 0, so it will be equal to 1. So the gamma function for x equals to 1 equals to e to the power minus t dt, here, this one. And if you integrate this, you get the result equals to 1. So gamma function evaluated at 1 equals to 1. Now, we can write the gamma function for x plus 1. This is the definition. So instead of your x, you can actually substitute x plus 1 instead, and then rewrite the definition. So if we, instead of x, if we put x plus 1, you will get t to the power x. And this expression now looks similar to us, like in our previous examples. why don't we use the integration by parts we know from calculus for these type of integrals? So we can let this u to be equal to t to the power x, and then we know how to differentiate both sides. You get du, and take the derivative of the right hand side. You have x times t to the power x minus 1 dt, because the right hand side depends on t. Here x is our independent variable. And then for the remaining term, we'll assign this as dv and then solve for v. So once we identify what is u and what's v, we are almost done. Now we can write u times v here, and then we have minus v times du. And here you write your v and then du. And notice that we have this x, so we take it out, and we have t to the power x minus 1 dt. But remember, what we see here, this expression, is the definition of the gamma function for x. So I can write this as the gamma function x. So this gives us a nice relation between the gamma function evaluated at x plus 1 versus the gamma function x. We just multiply with this x, and we can rewrite the gamma function x plus 1 in terms of the gamma function evaluated at x. Now, by using this property, actually, if we consider integer values instead of x, because we have seen this is true for the general values of x, which can be non-integer as well, but this is also going to be true for the integers. And if we do so, we can represent the gamma function n plus 1 as n times gamma n, and then keep substituting. So instead of this expression, you can substitute this term. And then instead of this expression, you can substitute this term. And then if you just keep substituting these values, you will get a multiplication of all these integers up to gamma of 1. And we have already calculated that the gamma function 1 equals to 1. So in other words, gamma function n plus 1, where this n is an integer, we can write this as n factorial. For some values, for example, if x equals to 1/2, we can write down the gamma function of 1 over 2. This integral is equal to the square root of the number pi. So actually, we can use this property for the gamma function of 1/2 in order to calculate various values, such as for gamma function 5 over 2, or for the gamma function 7 over 2. For these kind of values, we can easily write this using this property here, because this property, we can represent x plus 1 in terms of x times the gamma of x. So for example, if x plus 1, so if this is our x plus 1, this means our x in this case is 3 over 2. So we can rewrite this in terms of 3 over 2. So using this property, we are able to write this expression in terms of 3 over 2. But you can also repeat this. Again, going by subtracting each time the integer 1, and you can consider now this is your x plus 1, right? Just in order to use this property star. Now, if this is my x plus 1, basically my x is 1/2, so I can write this as 1/2 times gamma of 1/2. So it brings us all the way to the gamma of 1/2. Again, from calculus, we know that this is equal to the square root of pi. So we just substitute, and we can obtain the gamma function evaluated at 5/2 is actually equal to 3 times square root of pi over 4. Okay, so these are the examples that we considered for calculation of the Laplace transform. Thank you for watching.